Hello everyone, this is Lakshmi. Welcome to my channel Lakshmi Lucky. Okay, we are discussing in Riemann integration some theorems and problems right now. So today I am discussing one more theorem, very important in this Riemann integration. Yeah, so many times repeated question. Here given the statement has f be a bounded function on closed interval a comma b, and p and q, these two are partitions on this interval has given and p is contained in q. Then we need to prove this in equation. LFP is less than or equal to LFQ. It is less than or equal to UFQ. It is less than or equal to UFP. That means lower Riemann sum less than or equal to lower Riemann sum in terms of in partition Q. Here upper Riemann sum in partition Q. This is upper Riemann sum with partition P. Okay. Anyway, we'll show this in equation So what has given here? F is nothing but bounded function on the closed interval a comma b. Right now that you should take it is bounded function on this interval. So always it is bounded means should be exist infimum as well as supremum. Right now as well as first of all we need to take in this partitions right now. So we have two partitions are there. We'll consider P and Q be two partitions on the interval a comma b. Okay. So it has in this Q has only one more than U then partition P So that means it should be satisfies the conditions P is contained in Q, subset of or equal to Q, right now. So partitions I am defining. Partition P is nothing but set of all those elements of initial value A is equal to T0, T1, T2, so on, Tk minus 1, Tk, Tn minus 1, Tn is equal to B. This is the partition P. Okay. Similarly, you should take one more partition that is Q we are defining. It is also nothing but the set of all those elements of A is equal to T0, T1, T2, so on, Tk minus 1 and Tk. In between Tk minus 1, Tk, we have one more extra element is there now, that is U we are taking. Okay. And up to so on Tn minus 1, Tn. Tn obviously should be equal to B. This is the partition Q. Okay. So in this upper and lower Darboux sums for in this case P and Q same except in this subinterval Tk minus 1 comma Tk right now. So Tk minus 1 Tk is the subinterval of closed interval a comma b. So lower and upper Darboux sums for P is nothing but given as lower Darboux sum we are taking LFP. It should be is equal to infimum value small m we are denoting small m of f comma close interval subinterval Tk minus 1 comma Tk, and its length is nothing but what is there Tk minus 1 upper limit minus lower limit. Is it clear Make this equation 1. And upper Darboux sum is nothing but UFP, that should be is equal to capital M into f comma Tk minus 1 comma Tk, that subinterval only we are taking, and into length of the interval upper limit minus lower limit Tk minus 1. Is it clear So this is you should take equation 2 So the lower and upper Darboux sums for Q is nothing but this is for P and similarly we need to define in partition Q also. Okay. So same as upper and lower Darboux sums for P for Q. So it is nothing but given as lower Darboux sum for Q. LFQ is equal to same as it is like here small m of f comma Tk minus 1 comma U, because here elements are nothing but Tk minus 1 comma U comma Tk is there So these two are nothing but divided into two parts subintervals Tk minus 1 comma U and U comma Tk. So that's what sum of two intervals you should take. LFQ is nothing but m of f comma Tk minus 1 comma U, one of the subinterval, into length of the interval this one U minus Tk minus 1. Okay. Plus m of f comma u comma k, second subinterval, into its length of the interval ma tk minus u. Okay, this is lower Darboux sum for the partition Q. Similarly, upper Darboux sum for the partition Q also. Here UFQ, it should be is equal to capital M of f comma tk minus 1 comma u, same that intervals, into length of this interval u minus tk minus 1 plus m into f comma second subinterval ma u comma tk you should take. Its length of the interval tk minus u. Okay, we'll continue this. Yes. So here we have 4 equations are there ma. Now subtracting from equation 1 and 3 and 2 and 4 you should take ma. I am taking first subtracting from 1 from 3. So LFQ minus LFP, that should be is equal to lower Riemann sum with partition Q. We have small m of same conditions, write down ma, m into f comma tk minus 1 comma u into u minus tk minus 1, already we defined right now. Those only you should substitute instead of LFQ and LFP. Okay, we are substituting here, plus m into f of u comma tk minus u, minus LFP is nothing but m into f comma tk minus 1 comma tk into tk minus 1. Okay, and this should be is equal to ma, here this term as it is write down here, and second term also as it is you should write ma, minus m into here this term is there no, f comma tk minus 1 comma tk into here length of the interval tk minus 1 is there. In between tk and tk minus 1, for our convenience I am adding and subtracting. One more extra element is there now, that is I am taking minus u plus u. Okay, so length of the interval till here tk minus 1 comma u, one of the interval length, and u minus tk minus 1, one of the length. Okay, so in the next step ma, this is as it is write down till here. Okay, I am simplifying from here, minus m into m of f comma tk minus 1 comma tk into tk minus 1 tk minus u, one of the term you should take, and plus m into this term f comma tk minus 1 comma u into u minus tk minus 1. Okay, so we are splitting that condition, and in this case ma, yes, we have this condition no. So actually we know that this condition LFP, left side condition is there na, this is always non-negative, so that is greater than or equal to 0. So LHS is nothing but non-negative, means that is greater than or equal to 0, means what we can write, LFQ is greater than or equal to LFP, because this minus term I am taking on the right hand side. So here or it can be written as ma, LFP is less than or equal to LFQ also. So make this equation 5. So by using 1 and 3 equations we got LFP is less than or equal to LFQ right now, and from equations 2 and 4 we should get UFQ is less than or equal to UFP. Okay, so make this equation 6 ma. So and also here any partition and any subinterval, the lower Darboux sum cannot exceed upper Darboux sum. So that's what we can take from this. LFP is less than or equal to UFP and LFQ is less than or equal to UFQ we can write ma, from these two equations also. So from equation 5th, 6th and 7th, 8th, from these 4 equations we should get the inequation ma. Okay, LFQ, this means 5th equation, LFP is less than or equal to LFQ, it is less than or equal to this one, it is less than or equal to this condition. See here, LFP is less than or equal to what is there ma, UFP, and in this LFQ is less than or equal to UFQ. So from these 4 equations we should get LFP less than or equal to LFQ, it is less than or equal to UFQ, it is less than or equal to UFP. This is the inequality case. Okay, this is the required solution. Note this theorem. Yes. Next theorem. Here the statement has given, if f is a bounded function on closed interval a comma b, then prove LF is less than or equal to UF under usual notations. Okay. So here f is nothing but bounded function and this interval has given ma, obviously should be exist infimum and supremum in this interval, and we need to prove here lower Riemann sum is less than or equal to upper Riemann sum. Simply LFP or LF both are same, UFP or UF simply we can write. So in this we need to prove this inequation LF is less than or equal to UF. Okay. For 4 marks it is important anyway. Given that here f is nothing but bounded function on closed interval a comma b. Okay. So for the partition bounded function means in this p and q be any two partitions on closed interval a comma b, and already we have LFP is less than or equal to UFP by the previous inequation. Yes, no? So now we will define these two partitions P and Q. P is nothing but set of all those elements of A is equal to T0, T1, so on, Tk minus 1, Tk, so on, Tkn minus 1, Tn should be equal to B. And similarly, second partition Q, it is also nothing but set of all those elements of A is equal to T0, T1, so on, Tk minus 1, U, Tk, Tn minus 1, Tn is equal to B. In this, extra one element should be exist. So from this equation here, LFP is nothing but what it is a lower bound, right now. So the set UFQ where Q is nothing but partition of closed interval a comma b, right now. So that means LFP is nothing but less than or equal to greatest lower bound of upper Riemann sum. LFP is nothing but less than or equal to greatest lower bound of upper Riemann sum for the partition Q. That means we can define LFP is less than or equal to greatest lower bound means infimum of the set of all those elements of UFQ where Q is a partition of closed interval a comma b. Okay, and that means LFP is less than or equal to this total set is nothing but simply we can write UF. Okay, make that equation 2. And from this equation UF here UF is there on the right hand side. UF is nothing but upper bound for the set LFP where P is the partition of closed interval a comma b. That means UF is greater than or equal to least upper bound of LFP. Least upper bound of LFP means it is greater than or equal to least upper bound means what supremum, right now? Supremum of the set of all those elements of LFP where P is nothing but partition of closed interval a comma b. P belongs to closed interval a comma b means it is a partition on the closed interval a comma b only. Okay, that means UF is greater than or equal to this total set. Supremum of this total set is nothing but LF only. Or it can be written as LF is less than or equal to UF. Okay, this is also required solution. Very important for 4 marks I am saying. Note this theorem also. Prepare well. Thank you.